Welcome back everyone. In this lecture I will construct the irreducible representations of Sn. So, let us begin with the definition of tabloid. So, let us recall. So, we defined all these lambda tableaus. We actually define an equivalence relation on this set of lambda tableaus as follows. So, we say that a lambda tableau T1 is equivalent to another lambda tableau T2 if they have same set of entries in each row. If they have same set of entries in each row. Okay. So, this is an equivalence relation that is easy to verify, and this relation gives some equivalence classes of lambda tableaus. Those equivalence classes, they are called lambda tabloid. So, lambda tabloid is nothing but a tilde equivalence class of lambda tableau. Okay. So, this means if I am fixing a lambda tableau, and if you just permute if you fix a row and permute the entries, it is going to give equivalent lambda tableau, and we collect all of them as one equivalence class. That is what we are calling it as lambda tabloid. And in particularly what we can do, since we are allowed to permute among entries of each rows, so we can always write the entries in the increasing order. For example, if we take this 3 1 2, let us say 3 2 1 and then 5 4, this lambda tableau. So, it is indeed equivalent to. So, I can actually fix a row and then permute the entries among them, and similarly I can fix row 2 and then permute the entries. So, now you can easily see that this is naturally equivalent to the following tableau, where we have rearranged the entries in the increasing order. So, this is something we can always do. And if we take this all possible set of lambda tabloids, and we are going to define this symmetric group action on that, and that is actually going to give action on the span of these tabloids, and that space we call it m lambda, which is very important space for us. So, here is the lemma. So, we already have the action of Sn on the set of lambda tableaus, and we just realize that that induces a well defined action of Sn on this set of lambda tabloids. So, how do we check this? So, we need to prove that whenever T1 is related to T2 and sigma is in Sn, then sigma T1 must be related to sigma T2. So, recall that the way we defined the action. So, if I start with the tableau, let us call it T. So, let us say it has some entries here, A1 to A lambda 1, and then like A2 to some A2 lambda 2 and so on. So, now given sigma in Sn, the sigma of T is defined to be, you just apply sigma on each entries of these tableaus. So, that means you apply sigma A11 and so on, and then sigma so sigma from Sn acting on this T by permuting each entry of this given tableau T, Now, we want to claim that this action is indeed induces a well defined action on the set of lambda tabloids. So, for that what we need to prove, suppose if you have T1 related to T2 with respect to the defining relation that we defined before, and sigma is an element of Sn, then we check that sigma T1 is also related to sigma T2. So, in particular we have a well defined action of Sn on this set of tabloids, so which is denoted by T lambda. So, this T upper lambda is the set of lambda tabloids, and so from this we can see that Sn acts on this T lambda. Okay. So, let us check this statement. Assume that T1 and T2 are related. So, that means what? That means if I fix a row, so if I look at T1, so let us say I am looking at the ith row, so it will have some entries, let us say A1, A2 etc., some AR. Okay, this is the ith row of T1, let us say, and then the T2 is the ith row is obtained by just permuting some of these entries that is there in ith row of T1. So, you have this, again the size of this should be R, and then you will have some AI1, AI2 and so on AIR. So, this AI1 etc. AIR is simply some permutation of this A1 etc. AR. So, this is how the relation actually defined, because we said that T1 and T2 are related if they have same set of entries in each row. So, that means if I read it at the ith row level, then this set A1 etc. AR is same as this set AI1 etc. AIR. So, these two are same. So, now to show that sigma T1 related to sigma T2, we must show that whenever Ij are in the same row of sigma T1, if and only if they are in the same row of sigma T2. So, that means so let's take, okay, maybe I will relabel the index. So, let us say P and Q are in same row as row of, let us say sigma T1, then we want to show that if and only if P and Q they are in the same row of sigma T2. So, this is what we need to prove. So, now it is easy to see that if P Q are in the same row of sigma T1, then that would imply that if and only if, so if you apply sigma inverse of P and sigma inverse of Q, so they are supposed to be in the same row of T1, because sigma just applied on each entry of the tableau. So, if you just if you P and Q stays here, so let us say, so P is somewhere here and then Q is somewhere here. So, yeah, inside sigma T1. So, if this is sigma T1, then this is P and this is Q. Then when you apply sigma inverse, then the same position only in this position only sigma inverse of P and sigma inverse of Q lie in T1. Okay. So, that is very clear. So, that means since T1 and T2 are related, that would imply that if and only if sigma inverse P and sigma inverse Q, so they are in the same row of T2. Okay. So, this is in the same row of T1 and sigma inverse P, sigma inverse Q, they must be in the same row of T2 since T1 and T2 are related. So, the rows of T1 and rows of T2 they are same. So, that means they should be in the same row. So, now if you apply sigma, then you can see that P and Q must be in the same row of sigma T2, because we are simply applying sigma to T2. So, that says that whenever PQ are in the same row of sigma T1, if and only if PQ are in the same row of sigma T2. So, that means T1 related to T2 if and only if sigma T1 related to sigma T2. So, that means we have an action of Sn on T lambda. So, now we are going to take this action and we call this m lambda to be the C span of these tabloids T lambda. That means you take the free vector space spanned by T lambda. So, this is the free vector space spanned by T lambda over C. So, this is the space, and since Sn acts on T lambda, so that would imply that Sn acts on this m lambda. So, we have a natural representation, we call that representation phi lambda. So, phi lambda is the representation where Sn acts on this m lambda, which is given by the previous in the previous page. Okay. So, basically recall that the way this is going to act, let us do some example. For example, if I take something like this, so let us look at something 3 by 3, 3, 2. So, this is a partition of 5. So, now I want to just take some 3, 2, let us say 4, 1 and 5. So, this is my let us say the tableau. So, now if I am looking at the equivalence class, then you can see that this is equivalent to the following tableau. So, you can rearrange like T 2, 3, 4 and then you can also rearrange this as 1, 5. Okay. So, since the equivalence class of this lambda tableau, so they do not really see the way we write the entries in the row. So, we are allowed to permute entries of each row and then we can always write it in the increasing order, okay, at each row. So, now you can see that if I take some sigma from this S5, for example, we can take sigma to be let us say 1 4 and then 2 3. Okay, maybe let me just take 1 4. So, then the way this sigma acts on this class, so this is going to act entry wise. So, this is going to be a class. So, what we do? So, it is going to be just a sigma t. So, what is sigma t? You can see that this is same as, so 1 goes to 4 and then 4 goes to 1, all other elements are going to be fixed. So, I can just either apply it on this or apply it on this. So, let us see what happens if we apply it on the first one. So, you get exactly, so 3 stays as it is, 2 stays as it is, 4 becomes 1, 1 becomes 4 and 5 stays as it is. But this is same as, so we want to say, so let us apply it on this. So, then we get so 2 stays as it is, 3 stays as it is, 4 goes 1, 1 goes to 4 and 5 will be this. So, then you want this to be equivalent to 2 3 1 and 4 5, which is true. Okay. So, that means we have a well defined action of Sn on this space of tabloids, lambda tabloids. So, now we want to actually make use of this in order to actually get the definition of irreducible representations. Okay, so first let me actually tell you like what happens in the background, then it will be clear like how to define this irreducible representation. So, if we think about it in terms of the dominance order, so we can see that this m lambda, since this being actually a 5 dimensional representation of Sn, so one can easily see that. So, the dimension of this representation is given by this quotient of this stabilizer S lambda. Okay. So, let us look at this, the dimension. So, this is exactly the cardinality of Sn divided by the cardinality of S lambda. So, what is S lambda? S lambda is the Young group associated with this partition lambda. So, first observation is that the action of Sn on this lambda tabloids, that is indeed transitive, because it was already transitive on the lambda tabloids. So, the action of Sn on the set of lambda tableau is transitive, and that would imply that the action of Sn on T lambda is also transitive. So, since the action of Sn on T lambda is transitive, to find the dimension of m lambda, so it is enough to find the cardinality of T lambda, but since the action is transitive, so it is enough to pick an element. So, that is the element we already defined, we take it to be T lambda. So, this equivalence class inside T lambda, and then look at its stabilizer. So, recall that T lambda is obtained by taking this particular tableau where we fill 1 to lambda 1 in the first row, and then lambda 1 plus 1 etc., lambda 1 plus lambda 2 in the second row, and so on. So, at the end we will have something like this, lambda 1 plus etc. plus lambda L minus 1 plus 1 up to the total n. So, this particular tableau we called it as T lambda. So, we can fix this tableau and then use this tableau to obtain all other other tableaus. So, now using this transitive action, you can see that if we are interested in this the set of elements T lambda. So, this is will be given by Sn acting on this T subscript lambda. So, now that means using the group actions you can see that the cardinality of this T lambda is going to be the cardinality of the group divided by the stabilizer of this T lambda. But the stabilizer of this T lambda, since the group is acting by permuting each entries, you can see that the stabilizer is nothing but the product of the following groups. So, the stabilizer, which is S lambda, of T lambda is exactly given by, you take this S 1 to lambda 1 cross etc. cross S lambda 1 plus etc. lambda L minus 1 plus 1 etc. lambda 1 plus etc. plus lambda L, which is n. Okay. So, the stabilizer corresponds to the Young subgroup. So, this is called the Young subgroup corresponding to lambda. So, now it is very clear that the cardinality of this M subgroup is nothing but given by lambda 1 factorial times lambda 2 factorial etcetera lambda L factorial. So, that means the cardinality of this T lambda is given by n factorial divided by lambda 1 factorial etcetera lambda L factorial. So, this is exactly the dimension of our M lambda. So, this is 5 dimensional and we have very explicit formula for the dimension. But now, since any 5 dimensional representation can be written as direct sum of irreducible representations, so one should be able to actually write this M lambda as direct sum of irreducibles. So, indeed what happens if we actually we know that already the set of conjugacy classes of symmetric group, they will be an indexing set for the set of irreducible representations. So, now given lambda, which is the cycle type of the conjugacy class, which is the partition of n, if we denote this S lambda to be the irreducible representation corresponding to lambda. So, then what one can prove that this M lambda is always can be written as S lambda direct sum of S mu with the multiplicities, we call it as K mu lambda, where the mu runs over all possible elements, that is partitions which dominate lambda. Okay. And these multiplicities of S mu inside M lambda, so they are called Koska numbers. And it is an important problem in representation theory to actually get explicit formula for this Koska numbers and so on. Okay, this is something ultimately we want to prove. Okay, so I am just giving some heads up. So, given lambda partition, we denote this S lambda to be the corresponding irreducible representation of lambda, and we will see that the representation that we have defined using these tabloids, and that will always decomposes as this S lambda direct sum, this some S mu's with some multiplicities K mu lambda. This K mu lambda, they are the Koska numbers. So, that means if we use this dominance order, so we have some way to actually slice off this M lambda to get this S lambda. So, how do we actually do this? So, if you just assume this, then you can see that this S lambda perp inside this M lambda should corresponds to this part. So, that means to get this S lambda, somehow we take all possible copies of S mu where mu is not equal to lambda, and then slice them off, and then we get this S lambda. Okay. But instead of doing all those things, we straight away give the definition and then prove that this is what happens indeed inside M lambda. Okay. So, let us actually look at the definition of S lambda, but before that we need to actually understand these representations M lambda in more detailed way. So, for that let us do some examples. So, I am going to actually give you some small examples where we can actually explicitly describe what happens to M lambda. So, let us take lambda to be a single partition n. So, then in terms of the diagram, you can see that this is nothing but given by this single row with the n boxes. So, now if you look at this lambda tabloid, So, then you can see that since there is only one row, so the lambda tabloid, the T lambda is going to be just one single tabloid, which is corresponding to the class which is filled as 1 to n. Okay, so this is the class that will survive. Okay, so that means this m lambda, the span of this particular tabloid. So let me not just put this bracket. So that means this is just a one dimensional representation. And so what will be the action? You can see that whenever sigma is there inside your Sn, then sigma simply will permute the entries of 1 to n. So, sigma will act on this 1 to n by just permuting sigma 1 etc. sigma n. But up to equivalence class, you can see that the equivalence class of this is exactly same as the equivalent class of this 1 to n, because we are allowed to permute the entries of rows. Okay. So, in this case we get one dimensional trivial representation. So, now let us look at some non-trivial example. Take lambda to be n minus 1 comma 1. So, that means you have n minus 1 boxes here and then 1 box here. So, now what are all the lambda tabloids that we get? So, it is clear that the T lambda is in bijection with actually. So, let us try to understand what happens to the equivalence relation. So, if we take two lambda tableau, they are equivalent if and only if they have the same entry in the second row, because there is only one entry that you can put it here. So, that entry determines actually the lambda tabloid. So, that means there are exactly n number of lambda tabloids that you can actually make, because so given let us say lambda tabloid. So, the lambda tabloid will look like something like this, a1 to some a n minus 1 and then some entry here. Okay, let us call it star. So, then you can see that basically this lambda tabloid corresponds to that star only, and once we know the star, we can remove that star from 1 to n and then keep that star here in this second row, and remaining entries you can fill it in the first row, and then permuting them will not change anything. So, that means the lambda tabloids in this case corresponds to picking just one entry in the second row. So, that means the lambda tabloids, they are in 1 to 1 correspondence with this set 1 to n. So, given each entry, we will be able to create one lambda tabloid. So, that means what? So, how the action is defined? So, if I fix a lambda tabloid, let us call it this a1 etc. a n minus 1, and then you have this unique picked element a n. So, now sigma is going to act on this as sigma a1 etc. sigma a n minus 1 and sigma a n. Okay, so, this is how sigma is going to act. So, now if you think about it, so that means so this is going to indeed, so given this I, so we can create this lambda tabloid by putting this I here, and then the remaining entries, for example, you can just put it here. So, 1 2 let us say, so we have this I here which we remove, and the remaining entries we keep it. So, this is the tabloid that I am going to take for given I, and this if you call it as E I, then sigma ei is going to be exactly E sigma I. Okay. So, that means the representation that we get here is indeed regular representation of the symmetric group Sn. The regular representation is nothing but the symmetric group acting on this n dimensional space by permuting the coordinates. So, Ei will go to E sigma I. The same type of representation is what we are getting here in this case. Okay. So, when lambda is indeed non-trivial. So, if lambda is not equal to the single partition, then we will start getting actually non-trivial representations. So, we will see that this m lambda, the dimension is going to be actually more than 1. Okay. So, maybe I will leave it to you to think about it, but it is important to understand how to work with this m lambdas. Okay, I will stop here and I will complete the construction of irreducible representations in the next class.